are the sum, difference, product, and the quotient at A. In this case, we certainly need more hypothesis, means G of A is non-zero. This is because of the limit laws. If F and G are continuous at A, okay. Then the limit of these two functions exists. This one is f of a, and this one is g of a. Therefore, the limit of the sum of the two functions at a also exists, which is the sum of the limits of these two functions at a. And this is exactly the sum of these two functions at evaluated a. By definition, we can find this limit by direct substitution, by letting x be a. So, if for the difference we just replace plus by a minus and obtain this one. Okay, by Leibniz laws. So once we have a new concept, a new terminology, we always, not usually, okay, usually, in fact, always consider the new object, the relationship between the new one and the old ones. Okay. So continuity also preserves operations. If we replace continuity at A from one side, from the right or from the left, and all conclusions still valid. Still valid. Okay. And if we replace at A with on some interval, then the conclusion is also the sum, difference, product, and the quotient are continuous on that interval I. Okay, interval I. 好，所以说知道连续以后，假设两个函数都在 A 点连续，那么这两个函数的和差积商也在 A 点连续，这完全是根据极限定律所得的啊，就可以看得出来。把它改成单边极限也对，把它改成在某个区间上面，这个叙述仍然是成立的啊。So these observations quite easy to follow, to understand. I don't want to skip this detailed statements because I think in the future some maybe advanced knowledge, they are all based on these fundamental details. Okay, continuity. And we also have limit. Then there is a we can pose this problem. Under what condition or conditions, if we have a composite function, this limit can put inside this in front of G. Under what condition or conditions? Okay, the answer of this can be obtained in this way. Now, suppose G, the limit of G at some point A is the number L. Means G may be defined or undefined at A, but is defined on some neighborhood of A. And the values of G on this small open interval may be very close L here. Maybe from left, maybe on the right, maybe both. Okay. Suppose F at the number L is defined. See, F of this one. So F should be defined as F. Means FL should be defined. And for the limit, means F can map points nearby L to maybe inside some small neighborhood of F of L. This is exactly saying F is continuous at L. If F is continuous at L, then the limit of F at L is F of L. So we obtain this condition. Suppose F is right? So this is a limit theorem about a composite function. Composite function. A consequence or a corollary of this one is, suppose both F and G are continuous. For example, G is continuous at A, means L can be replaced by G of A. And F is also continuous at G of A, then this value should be F of G of A. So we obtained a corollary or a consequence, direct consequence of that statement. If G is continuous at some number A, and F is continuous at G of A, then the conclusion is F circle G is continuous at the number A. That is the limit of F of G of X. When X approaches A equals limit, put limit inside this parenthesis, limit when x approaches it, g of x is exactly g of a. Okay. So, in short, or roughly speaking, this result can be described in this way. A continuous function of a continuous function is continuous. Okay. F of g, continuous function of a continuous function is continuous, roughly speaking. Not only at some point, but also on some intervals. Okay. On some interval or intervals. This yes, they are all theorems in our textbook. You can read the textbook and find the exact. This is theorem 8. Number 8 theorem. Number 8. In our textbook. Yes, this is number 9 theorem. You can find all the statements in our textbook, okay? Very well. I think almost 10 a.m., so we had better take a short break. Okay, thanks.